All right, let's get this. Okay, so claim evidence reasoning, it's back and it's going to keep coming back. But this week we're talking about collisions, which we're going to be seeing these words again. We're going to be seeing force, we're also going to see mass and acceleration, but we're actually going to be breaking acceleration into two individual parts, velocity and time of impact. So here's the breakdown of today. We're going to review what CER is, claim evidence reasoning. We're going to talk about collisions and things that you should already know. Three, we're going to talk about the math behind collisions. So we've already talked about force equals mass times acceleration, but it's technically the same as this fancy looking one here. It's force equals mass times velocity over time, which we'll get into in just a second, but it's pretty simple. And number four is CER, more claim evidence reasoning, with some real life applications of collisions with cars using this formula, looking at the math, and more writing this week. So here we go. Just to review, what is CER? CER stands for claim, evidence, and reasoning. Most of the time, we just stop at the claim, but when I ask you to write in this class, I'm going to need you to do claim, evidence, and reasoning. So just to review, what is the claim? The claim is just stating the answer to the question. Again, this is mostly where we stop when I just need a one sentence answer, but when writing a paragraph in science, we need more than that. So what comes next? It's evidence. Evidence is observations. In this case today, it's going to be data or other research. If I ask you to search something online, that could be evidence also. But most of the time, it's just going to be data in the form of quantitative data, which is numbers. We're going to put numbers and units in here. And the next one is reasoning. Reasoning is where we throw in the scientific principle that we've been talking about this week or that you know about. And again, it's Newton's second law, but we're going to get a little deeper into Newton's second law. So, expectations in science classroom. When I ask you to write a paragraph or a lab write up, it is always claim, answer the question, evidence, need at least two pieces of evidence, if not more, and reasoning. Okay, so what we know so far. Last week we talked about Newton's second law, which is force equals mass times acceleration. Just a reminder, a force is a push, like this is happening here, or it could even be a pull, like gravity. Gravity is pulling you down to the earth right now, and if you jump up, the earth will pull you right back down. Its unit is the N, or newtons. N for newtons. Mass is the amount of stuff in an object, and if you check out this cat, it's got quite a bit of stuff. So you'd say that this is a massive cat. It is the amount of stuff in an object, and its unit is the kilograms. The last one is acceleration. This is how fast you speed up, technically how fast you slow down, or you're changing directions. Its unit was really weird, meters per second, and we're going to actually dig into that on the next slide. So what really is acceleration? I already told you it's to speed up, to slow down, or to change directions. But if we check out the unit, we can actually break it down into smaller things because this is a really fat unit. What if we just took the first two, which is meters per second? Meters per second. That would be velocity, which is the same thing as speed, but with a direction. In Spanish, it's like velocidad for speed. Okay, speed and velocity are pretty much the exact same thing. For this class, we're going to pretend it's pretty much the exact same thing. I'm not going to test you on the difference of the two, so every time you see the word velocity, you can pretty much assume I'm just talking about the speed. Now, in science class, we use meters per second, but in the rest of your life, you're going to probably use miles per hour because we live in the United States. So say you're going 30 miles per hour, it's miles divided by hours. In this case, it's meters divided by second. So if we use miles per hour, if you're going 30 miles per hour, you went 30 miles in an hour. If you were going 60 miles per hour on the highway, it would take you an hour to go 60 miles. That's how speed works, okay? It's a distance over a time. All right, so that's the first bit of acceleration. It's these first two numbers, but the other one is really weird. This S right here is how fast you speed up, slow down, or change directions. And for this exact thing we're doing right now, collisions, things running into each other, it's the time of impact. How long did the impact take? And for this one, it almost takes about a second, maybe a second and a half. Its unit is simply seconds. That's the second S in this unit here. So That's acceleration. It's just velocity divided by time of impact. So, slight clarification for our knowledge. We're still technically talking about Newton's second law, but we're breaking it down a little bit more by looking at it like this. Force equals mass times velocity divided by the time of the impact. So, a push or a pull equals how big an object is times how fast it's going divided by how long a collision took to happen. How long did it take you to run your car into a bridge? Which kind of gives us to our next thing. Let's look at some relationships, and we're going to be looking at cars running into bridges. So I'm going to write all these claims and these evidence and these reasonings because it's going to keep coming back and it's going to become automatic for you in this class. So what's the relationship between force and mass? And if you paid any bit of attention last week, you should already know. What happens when the mass gets bigger? What happens to force? If something hits you with the same amount of mass, or sorry, a bigger amount of mass, is it going to hurt more? Yeah, you should know this. All right. So, what's the relationship between mass and force? So, let's see what happens. Using the evidence from the data above here, make a claim about which is the safest car and the relationship between mass, velocity, time of impact, and force based on Newton's second law. That's a lot going on in this question. That's why I'm asking you to write a paragraph. So here we go. We're going to look at the mass of each one of these cars. We have a Honda Civic there. We have a Tesla. It's going to be our white car, and our Subaru, which is going to be our blue car. I looked up the masses of each one of these cars, and I put them on the table here in kilograms. And if we look at them, um, it looks like our Subaru is our biggest mass here, and our Honda Civic is the least massive. It's the lightest car. So if all three of these were to hit this bridge, so Honda Civic, Tesla, and Subaru, which one's going to do more damage to the bridge? The Civic, which is the lightest one, the Tesla, which is in the middle, or the Subaru, which is the fattest car, the more massive car? If you said the Subaru, you're right. The Subaru, boom, hits this bridge and it's going to hit it with more force because it is the fattest car. And you can see that on the graph here. Subaru, most amount of force. Honda Civic, least amount of force. So let's look at these numbers. Actually, we don't need to look at the numbers anymore. Let's just roll on to writing our claim. So according to table 1, the Honda is going to be the safest car because it has a direct relationship between mass and force and time of impact, or while the velocity and time of impact remain constant. There we go. We answered the question, but we need some evidence, and we have evidence. Let's use it. So if you remember, I told you just to find a section, a set of data, some data sets here. Just pick two. So we have the Honda Civic and we have the Subaru. Okay, Honda Civic and Subaru. So when the Honda Civic's mass was 1,250 kilograms, the velocity was 15.6 meters per second, and the impact or time of impact was 0.7 seconds, and the force was 278,571. When the Subaru's mass was 1,750, the velocity was 15.6 meters per second, and the time of impact was 0.7 seconds. The force was 390,000 newtons. That's just putting this into a sentence and putting this into a sentence. We're just listing off data to make a data set. Okay, the last bit is reasoning. So Newton's second law states force equals mass times velocity divided by time. So as mass increases, the force increases if the velocity and time of impact remain constant. Look at this. These numbers, they're exactly the same. So the velocity of these cars, they're going about 30 miles an hour. That is constant. Time of impact, they all hit the bridge. There's nothing to slow them down. They all had the same impact. Those are constant. All right. Let's try this again, but let's look at force and velocity. And again, if you were paying any attention last week, you should already know if something's going faster, should it have more or less force? Let's find out. So we're going to be looking at velocity this time. As velocity goes up, what's going to happen to force? So we have three cars here, and I made the graph ugly on purpose. I'll come back to that here in a second. So we have this Subaru, which seems to be going the slowest. Boom, hits the bridge. We have the Honda Civic. Boom, hits the bridge, but it's going a little faster. And this Tesla is zooming. Boom, hits it the fastest. Which one's going to hit with more force? Which one's going to do more damage to the bridge? If you said the Tesla, you're right. Your instincts are correct. But can we put that into words to answer this question here? Using the evidence from the data above, make a claim about which car is the safest. Which car would you rather be in hitting this bridge? If you said the Subaru, you're probably right, and that's the answer to this question. And the relationship between mass, velocity, time of impact, and force, based on Newton's second law, force equals mass times velocity divided by time. So here we go. Let's make an answer to this. According to table 1, the Subaru is the safest car. Oh, look at it. It is most definitely the safest car. It's going the slowest. Um, and there's a direct relationship between velocity and force, while mass and time of impact remain constant. So let's look at the numbers here because this did not make a pretty graph. I said I'd come back to this. Not every graph is going to allow you to have that cheat code that you got to see last week where they all went either up or they all went down. When they look something like this, you don't get to use the cheat code. You got to come up to the numbers and look. So let's look at the slowest car. There's the Subaru, and there's its numbers. It's pretty low compared to the fastest car, which is the Tesla, which is right here. It's going the fastest. So let's put these two data sets into sentences. Here we go. So the Tesla's mass was 1,250 kilograms. The velocity was to 23.4 meters per second, and the time of impact was 0.07, and the force was 417,857. Now it's for time for the Subaru. So Subaru time. The Subaru's mass was 1,250. The velocity was 7.8 meters per second. The time of impact was 0.7, and the force was 139,286. We did it. All right. That takes forever, but when you do it, you sound super smart because you are. All right. Reasoning. Time to sum it all up. Newton's second law states force equals mass times velocity over time. So as velocity increases, the force increases if the mass and time of impact remain constant. Just a reminder, check this out. I just pretended like all these cars weighed exactly the same for this scenario. Time of impact, the crashes were all the same hitting this thing, so we would call that constant. All right, make sure that you're using the word constant rather than saying it stayed the same. You sound smarter, and that's the correct way to say it in science class. Let's look at the last one. Wake up for this one, because this is definitely the most confusing of these, and it's the opposite. So if you're falling asleep on me, wake up for this right here. What's the relationship between force and time of impact? All right, force and how long the impact took. This one's going to be a weird one. By the way, it's a weird one because there's the division side. If you're math aware, anytime you divide by something, it's generally the opposite of what we normally see. So odds are we're going to see an inverse. So here we go. We don't have a pretty graph, so we don't get to use our cheat codes. But let's look at our hypothetical here. We have a Honda Civic hitting a bridge, and there's nothing in the way of it. It's just going to run, boom, hit the bridge. We have a Tesla who's going to hit these weird yellow things. And if you've ever seen these weird yellow things, they're always under bridges. These are called water barrels. They're full of disgusting old water. If you're interested, get on YouTube and watch people running into bridges. Maybe I shouldn't tell you to do that. Most of them survive because of the water barrels. When they hit these water barrels, it goes boom, 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 boom. And by the time they hit the bridge, they didn't cause much damage to the bridge, and odds are they walked away from it. Now, our last one here is our Subaru, and it's only going to hit one water barrel before it hits the bridge. So looking at these, the Honda Civic, it's going to hit the bridge in like zero point 0.1 of seconds. That's faster than you can probably snap your fingers. It's going to pow, hit it super fast. Whereas the Tesla, it takes about 3 seconds for it to go through all of these barrels before it actually hits the bridge. And the last one is the Subaru. And the Subaru hits the bridge in about 1 second because it takes it about 1 second to break through one of these barrels and finally hit the bridge. So which one do you think is going to have more force? The Honda Civic, the Tesla, or the Subaru? If you said the Honda Civic, you're probably right. You're definitely right. When it hits the bridge, it's going to hit with the most amount of force onto the bridge. It's going to cause some major damage to the bridge as well as whoever's in the car. So, looking at this, let's look. The Tesla has the lowest amount of force because it has the highest time of impact, whereas the lowest time of impact, zero point 0.1, has the highest amount of force. And look how much bigger it is. This one's 6,500 and this one is 195,000. I don't know if this was money, I would want this money compared to this money, but that's a huge jump for just not that big set of numbers. So when you divide by these tiny numbers, you're going to get some major effects. And you'll notice this, the more labs we do with this, changing time of impact is huge. And that's what we're going to be looking at this week is this crazy inverse. The bigger this number, the smaller this one. The smaller this one, the bigger this one. If you get anything from this video, it's that. It's an inverse. So according to table one, which one's the safest? The safest is going to be the Tesla. Tesla, lowest amount of force, is the safest because there's an inverse relationship between time of impact and force while mass and velocity remain constant. Again, we pretended like all the cars weighed the same, they were all going the same miles per hour, but they had different amounts of barrels. So the force is lower when you have more barrels to slow you down over a longer period of time. Evidence. Let's pick out some data sets. So let's just pick the Honda Civic and the Tesla and write these into sentences. So here we go. The Honda's mass was 1,250 kilograms. The velocity was 15.6 meters per second, and the time of impact was zero point 0.1 seconds, and the force was 195,000 newtons. The Tesla's mass was 1,250. The velocity was 15.6 meters per second, and the velocity or the time of impact was 3 seconds, and the force was 6,500 newtons. So reasoning. Newton's law states that force equals mass times velocity over time. So as the time of impact increases, the force decreases if the mass and velocity remain constant. Inverse relationship, increase, decrease. All the other ones were increase, increase. This one's an opposite, increase, decrease, inverse. So there it is. We're still talking about force equals mass times acceleration, but now we're going to be talking about collisions. And to do that, we really need to break acceleration into its pieces here, which is velocity over time. Remember, force is a push or a pull. Mass is the amount of stuff in an object. Velocity is just speed. It's how fast you're going. Time of impact is how long it took for the impact to actually happen. And putting these two together actually give you acceleration, which takes us back to Newton's second law, but it can be broken down even further. Here's your relationships. As the force increases, as the mass increases, the force increases. As the velocity increases, the force increases. As the time of impact increases, the force decreases. That's an inverse relationship. So, mass and force, direct. Velocity and force, direct. Time of impact and force, inverse relationship. That is all. Best of luck, ladies and gentlemen. Have a wonderful day. Goodbye.